All right, welcome to the final review for fall 2022. I'm just going to go through some notes I've prepared, work some problems. I'll break this video into smaller chunks to help it be digestible, and hopefully this will give you kind of a nice broad overview of the kinds of things that you need to be thinking about for the final exam. All right, so we started this course with the question, how long does algorithm A take to run? So how long, or I should say how fast, is algorithm A? And we immediately kind of came to the conclusion that this is the wrong question. Right? So one, this is the wrong question. There's a couple specific reasons. I mean, so one of them, that this question is too hardware dependent. It's too language dependent. It's too subtle details of implementation dependent. It's too operating system dependent, et cetera, et cetera. So our better question, we immediately discovered, was something like this. How does the running time of the algorithm scale with the size of the input? So how does speed scale with input size? And this led us to the use of this concept called big O and its friends big omega and big theta. So this leads to big O, big omega, well, I'll do big theta because I just drew it, and big omega. All right. And one of the ways you can kind of think of this is that big theta tells us something about the shape of the running time of an algorithm. So if I write T of n to be the running time, if T of n is running time, we say something like T of n is in big theta of some other function, f of n. And this means something like T of n is shaped like f of n when the n's get really large. So this means T is shaped like f when n is large. That's the key kind of insight. And I like to say when you zoom out on the plot, like if I plot T of n and f of n, and then I zoom out and squint, those two functions are going to look very, very similar. They'll essentially look like scaled copies of each other if one of them is big theta of the other. So what does this tell us? If I know that t is big theta of some function, what does this tell me? So what does big theta tell me? Well, there's this table that I did early on in the course, and I said, look, suppose T of n is big theta of, say, n. Then this tells me that doubling the input size approximately doubles the running time. So T of 2n approximately equals 2 times T of n. What if T of n is big theta of n squared? Then this tells me that T of 2n approximately quadruples the running time. All right, so it scales worse in some kind of quantifiable way than an algorithm that is T of that is big theta of n. All right, what if T of n is big theta of 2 to the n? Well, this tells me that T of 2n is approximately equal T of n squared, right? So you can see that the scaling gets really bad. And now you've seen a lot of algorithms that actually run in exponential time. You've implemented some, and we've talked a lot about these kind of broader complexity theory concepts. And so now hopefully you have a clearer perspective here of kind of what's going on. And yeah, this is actually kind of a cute one. I don't know that I did this one early in the course, but say I have T of n being big theta of, say, n to the n, something really terrible. Let's get my pen. T of n being big theta of, say, n to the n. Then this actually tells us that T of 2n is approximately equal to not just Tn squared, right? So definitely Tn squared, but then times 4 to the power of n. So we have this exponential factor multiplied onto an already squaring kind of a characteristic. And so that gives you a picture a little bit more vividly about why n to the n is has such bad scaling properties. All right, so the course is all about design and analysis, and the first part of the course we spent almost entirely on analysis. And so the overarching analysis technique went something like this. Analysis technique. Kind of once we had established that what we want to understand is orders of growth, is this big theta concept for running time, now we established this technique for actually taking an algorithm and doing this. So 1, you determine the input size parameter. Or multiple parameters to describe input size. Input size. Okay, so now after that you determined a basic operation. So an operation that kind of drives the slowness of the algorithm, drives the scaling properties of the algorithm. So you determine the basic operation. And so this operation is usually something that's on the inside of an innermost loop. Now and then there have to be more than one basic operation, and so you have to kind of say we're counting this thing and this thing if there's multiple loops that have multiple different kinds of things happening in them. But typically this isn't too hard to do. So now what you have to do is determine an expression for a t of n, and t of n is going to mean something slightly distinct from the running time. So now you want to determine an expression, a mathematical expression for t of n. And t of n is defined as the number of executions of the basic operation. Here, and I should have an s there as well. Executions of the basic op, parentheses s, with respect to n. Okay, typically, if it's an iterative algorithm, this is going to look like a sum. If it's non-recursive, typically some kind of a summation, I equals 1 to n, dot, dot, dot. If it's recursive, this is typically a recurrence relation. So something where there's a recursively defined running time. So once you've found this expression, now number 4 is you determine the order of growth. Determine the order of growth. Determine order of growth of t of n. And that's kind of the goal. The goal in the end is to find this order of growth and make sure that we know something about this. So here's an example, very simple example. We've got some algorithm. It takes in an input n. Now if n is greater than or equal to, n is less than or equal to 1, you return 0. Otherwise, you return the algo again, a recursive call to algo on n minus 1 plus n squared. All right. Now, how are we going to analyze this? Well, to analyze it, we observe, hey, n is just the input. So n is input size. Our basic operation is going to be essentially, in a recursive algorithm, the basic operation is often going to be either base cases or something that happens when you recurse. And so in this one, we'll call this plus our basic op. And so now we have to come up with, so now we have an input size, we have a basic operation. Now we have to come up with an expression for t of n. How many basic operations get executed? And so basically what we do here is we say, hey, look, here's a t of n. And t of n equals 1. There's one basic operation on this line, and then there's one recursive call on a problem of size n minus 1. So plus t of n minus 1. And so t of n here equals t of n minus 1 plus 1. And what if n is 1 or smaller? So if t of 1 then is 0. There's no additions to happen here. So this is t of 1 and t of 0, and no basic ops. All right, and I can also write, well, that's fine. T of 1 is equal to 0 is fine. That'll catch it. And now you know a bunch of techniques. I'm not going to run through these right now. There's lots and lots of examples of these back in the lecture videos from class. But you know lots of techniques to take this and convert it into or solve it and figure out what is this actual function. And basically what we see here is we've got something that is size n. It costs one basic operation and then shrinks by 1. And so that means it must shrink down, approximately n times, and each one of those corresponds to a basic operation. And so t of n has to be linear in its order of growth. So big theta of n in its order of growth.